Okay, so what I'm going to try to do in this talk is sort of piggyback on a couple of the talks we've already seen today, sort of bringing together some of the ideas we saw from the first talk, as well as Mariano's talk on the RHEM model and its application we'll talk about here, and some of the concepts that Ken just talked about. And so this is a paper that we have currently in revision with Rangeland Ecology and Management. There are about 20 authors on the actual paper. But today I'm just be using some experimental data to sort of support those concepts. A lot of the data coming through funding through the Joint Fire Science Program, in particular through the SAGE STEP project. And so as I started to think about the talk, I continuously try to convince myself that we all sort of agree hydrology matters. And then I'll talk to people from other disciplines. I'm a hydrologist myself, and oftentimes they'll say, well, why are we even concerned about hydrology on rangelands? And, and in some places we're not. But I do think we're starting to agree on it, and I think we have for a long time. If we just step back and look at sort of the rangeland health concepts that came out, even in this earlier paper from Dave Pike and others, these concepts here in terms of the rangeland health largely include aspects of hydrology, in particular soil and site stability, redistribution, and loss of soil resources. Hydrologic function is specifically mentioned there. And of course, a lot of the rangeland health indicators we look at are interpreted in a hydrologic context. So are there rills present, water flow patterns, and things of that nature. So I think, even across a lot of disciplines now, we pretty readily agree that hydrology is important. And I think the talks today have sort of tried to highlight that point as well. But it leads us to sort of the problem that we still have, is that many of the ecological site descriptions still are commonly void of hydrologic and erosion information, in particular vegetation and hydrology interactions. And that could be in part because we don't know what to put into the ecological site description or where to put it, how to come up with that information. So this talk largely today will be centered around that, and that's what our paper is about. Our specific objectives for the talk today, I'll review vegetation and hydrology interactions using some experimental data. We'll talk about how and where to include hydrologic data in an ecological site description in terms of suggestions that we have in our paper. And then I'll discuss sort of application of the RHEM model for populating this type of information in an ESD. So we know that vegetation and hydrology interactions are important. We know that for sort of a well-vegetated rangeland community, runoff and erosion rates are low. These are generally associated with a biotic control on that through the vegetation. Runoff and erosion largely occur through rain splash and sheet flow processes. On these types of systems, the runoff and erosion generally travels a very limited distance downslope before it's intercepted by vegetation or ground cover, where we have infiltration and deposition. Again, this is associated with a well-productive site. On the opposite end of the spectrum, where we have increases in bare ground, in many cases, we can get these concentrated flow paths formed during storms. This is a much more efficient transport system for rain splash and sheet flow detached sediment, as well as it can form these incisions and move sediment downslope at a much higher rate, or it's a better transport mechanism than these two processes. So we have these two opposite ends of the spectrum, one associated with sort of biotic control and then the sort of abiotic controlled system here. And we can conceptualize that in this model that we see here. On this x-axis, we have surface susceptibility. We can think of that as sort of a combination of all these variables that dictate the susceptibility of the surface to sediment detachment and transport. And then sort of all that dictating our overall hydrologic vulnerability. It's a function of surface susceptibility as well as the magnitude of the water input at the particular time or for a particular storm. And I kind of think of this in some ways as a hydrologic version of a state in transition model. We can use a sagebrush steppe site, for example, in the Great Basin that you see here. We can think of this as plotting in this area of the graph, essentially having a low surface susceptibility and low hydrologic vulnerability. And then as we shift to this other end of the spectrum, where we have expansive bare ground, high surface susceptibility, we would expect hydrologic vulnerability to be high. And again, that's associated with these processes. So on this end, we're looking at rain splash and sheet flow as our dominant processes. And then over here in this more degraded condition, concentrated flow becomes active. So we could start to link the vegetation and hydrology in, say, a conceptual model like this of hydrology, and then something like a state and transition model, thinking of these pictures as representing an abbreviated version of that. And I guess I also want to mention, so other things we would be interested in is there's some particular threshold for a particular site of interest where we see a change or shift in surface susceptibility that's going to lead us more to this state. And when we get here, can we shift it back through some conservation practice or restoration practice that essentially is strongly related to the vegetation and the hydrology interactions. So now what we'll do is step through some experimental data that sort of support the concepts I'm talking about, and then we'll move into talking about ESDs in particular. This is a sagebrush steppe site in the Great Basin. This is in southwestern Idaho. And at this site, Dr. Fred Pearson conducted some rainfall simulations at these 0.5 square meter scales and interspaces between shrubs and the few juniper that were there, as well as at individual shrub scale. And applying a high intensity storm, if we look in yellow here at the runoff rates, so at the small plot scale, you can see the runoff rates here, 30 to nearly 50 millimeters of runoff over the course of I think an hour rainfall simulation. But if we look at doing the same simulation over a 32.5 square meter scale, you can see runoff drops to 3 millimeters. So as we would expect, we're seeing a decrease in runoff over increasing spatial scales. Same thing for sediment. You can see the erosion here, cumulative sediment, and then sort of what happens over the larger scale. So a decrease in erosion with increasing plot scale in this study, as we would expect for sort of a well-vegetated site like this. So the site was burned in a prescribed fire as a fuel reduction treatment. We can see now what happens with runoff. So again, we have these small plots, 61 millimeters of runoff from shrubs, 44 from the interspace, but you can see it drops to 16 once we look at the measurements from the large plot scale. So an increase over the pre-fire levels, but still a decrease over increasing spatial scales. But it's a little bit different story when we disturb the site with fire and we look at erosion. So here are the erosion rates for the small plots, so 183 to 705 grams per square meter, and we're nearly at 1,000 grams per square meter for this particular storm that was applied in this case. So erosion is sort of increasing at least over the spatial scales that we measured here. And that's largely associated with a shift in the dominant runoff and erosion mechanisms, so concentrated flow becoming active here. So we can look at data from, let's see, 3 different years in this study, the same simulations. The runoff and erosion, or the erosion response, we can think of this here as representing erodibility, sort of a convoluted variable there, sediment divided by the amount of runoff. But if you think of this just as erodibility, we can see that it was pretty well related to bare ground. So the red being the year of the fire, the green being 1 year post-fire, and then so around 60% we see a threshold there for increased erosion, as well as the velocity of overland flow as measured in these experiments. But again, these relationships, they're associated with bare ground, but the bare ground is also associated with the formation of rills. If we look at the maximum number of rills in our plots, it decreased with time as the vegetation started to recover. And again, the runoff was associated with that too. So here by year 1, we still have enough runoff that we can get these concentrated flow paths and have the elevated erosion rates and higher velocity flows. But by year 2, we have very limited runoff and erosion's back to near pre-fire levels. So we start to see a disconnect in the connectivity of those processes across the hill slope. You can see how vegetation changed from year 1 to year 2, and you can see how erosion decreased by year 2 close to the pre-fire levels. So again, this is associated with the vegetation. We remove it, we increase the connectivity of processes, and as it comes back, we start to create a disconnect of those processes that are occurring. So that's the vegetation and hydrology interactions at play there. This is another common problem in the Great Basin is woodland encroachment into shrub steppe systems. As these trees encroach, it's fairly common, but not on every site. You can start to get a depletion of the understory vegetation. The shrub component can drop out. We can get these expansive areas of bare ground where runoff and erosion becomes a problem. We'll sort of step through some data for a number of sites, 3 different woodlands in the Great Basin. So for these sites, as we would expect for a degraded system, runoff and erosion sort of have this fairly linear relationship for a bunch of rainfall simulation work we did there. Again, these data are across 3 sites. We can see that there's some threshold of 50 to 60% bare ground where erosion starts to increase at an increasing rate. And again, that's associated with what happens in these little patches of bare ground where runoff starts to accumulate, form these concentrated flow paths, which then become a more efficient transport mechanism for sediment delivery from these plots. And you can observe this in large storms. We see this very active in our plots for rainfall simulation work. So what happens is we start to sort of investigate what happens, say, over a half square meter versus 13 square meter plots that we have. And what we see is that these runoff and erosion rates that we measure at the small plot scale, when we area weight them into, say, a large plot scale of 13 square meters and compare those to what we measured from the same simulations at this larger scale, we see that runoff really didn't change much across spatial scales. So we're almost getting the same amount of runoff at a large plot scale as we were this small plot scale, but erosion, the green bar for measured, was much greater than what we area weighted. So we're getting an increase in erosion across spatial scales without an increase in runoff. And it's largely because we're changing the mechanism of runoff. Over these larger scales, concentrated flow becomes active. It can't really form at this small plot scale. So it becomes active at this larger plot scale, and it's a more efficient transport mechanism, and we see this elevated erosion rate across plot scales. So again, some interaction of the vegetation and hydrology that's important for these sites. And then the next question is what happens when we burn it? You know, immediately post-fire and then over the long term. We can see there are obvious changes in vegetation there that we know are going to influence hydrology. And the hydrology influences the vegetation change as well through infiltration, increased soil water availability, and things of that nature. So we'll take a quick look at some data from fire. This is a western juniper site in Idaho that was burned by wildfire. We conducted rainfall simulations here as well. And again, if we look at sort of the pre-fire runoff and erosion rates from large plots, that's this line here, the blue being inner canopy areas between the trees. We see that we have this linear relationship that we had from the previous slide of other woodland sites. But after the fire, we get this sort of exponential deviation in the erosion versus runoff relationship. And again, this is associated with that connectivity that develops after fire. So even for a degraded site, we have an increased connectivity post-fire. We also have more sediment available after fire. There's a readily available supply of sediment, and concentrated flow processes kick in, starts to deliver that excess available sediment. And then we would expect this to sort of, this relationship to sort of change over time, but this is sort of that immediate post-fire period. Okay, so 2 years after fire, what happens? Well, you can see we get this sort of favorable herbaceous response in the inner canopy of this site. This was essentially almost all bare ground before the fire. And what happened, what we saw in these concentrated flow experiments that we run, where we release overland flow into the hill slope, is that in the unburned areas, we had these very clear and sized flow paths that you see here. And you can see the rates of erosion from the experiments that we run. The same experiments, 2 years after the fire, where we have this vegetation response, we can see there's a negligible incised flow path from the very same experiment, same flow rates that we release, and a much lower erosion rate. So we're starting to see a decreased connectivity of processes here associated with that vegetation change. This is another study by Dr. Pearson looking at western juniper site in the Steens, Oregon area, Steens Mountains of Oregon. At this site, there were various areas that were untreated juniper woodlands with extensive bare ground. There were other adjacent communities that had been cut 10 years before, and then another area that 20 years before. And we released overland flow at all these treatment areas. And you can see how erosion declined with these changes in vegetation cover. So again, making the point that the vegetation is strongly influencing the hydrology, and of course this vegetation shift is associated with changes in hydrology, improved infiltration, and soil water storage. And again, you can see how it sort of fits in this hydrologic conceptual model that again is also sort of strongly related to what we would build in a state and transition model. So now we'll talk briefly about ESDs and hydrology, and I'm not expecting us to go through the details of this table, of course. It's a bit cumbersome to look at. But basically what we have here are the feature areas within an ecological site description, and then these are the key elements within each of those feature areas. And all the yellow highlighted are basically variables that relate to hydrology. So just making the point that we already do consider hydrology important, it's just not always there in great detail. So how do we get more hydrologic information, and where do we put it? So we can think of this upper area here as being our inherent site characteristics, climate, soils, topography, and this lower area being more about the community dynamics. and structural and functional thresholds. This is really the area where we're suggesting that we include more hydrologic information. And we're going to do that through creation of a hydrologic functions table, trying to build a table that depicts all the relationships I've been talking about with experimental data, but also using the rangeland hydrology and erosion model to predict those sorts of responses. And then we can sort of integrate that information into the ecological site dynamics. In our paper, we go in detail about what all of this is. I'm not going to do that today, but essentially these are the types of data we think are needed to do what I'm going to discuss here. This information here helps us populate the rangeland hydrology and erosion model. It's already required in various areas of the ESD. And then this information down here is structural and functional thresholds, sort of qualitative data that we think we can infuse into a state and transition model. It's already done with vegetation, but can we add hydrologic components to that? And then I'm going to show specifically how we can predict this cumulative runoff and erosion rates or infiltration, basic hydrology information into an ESD. Again, you heard earlier talk today by Mariano going over sort of the details of the RHEM model. I'm not going to go into that here. We have several papers out that explain the model, and there's other information here available at the link. But basically, you can set this model to run for any of the different plant community phases of the states, or even for conservation practices if you know how the vegetation is going to change in the short run and in the long run. And it's populated with pretty basic data. So you select a climate station within the model, put in the soils information, the slope characteristics, and then canopy cover. And if you have that type of information for the different plant community phases, you could sort of populate this for an entire state and transition model, as well as for any conservation practices that you might apply within that. This is an example of a hydrologic functions table for sort of this plant community that I've been talking about here, or this site. It's an abbreviated version. We would have many other community phases on here. But basically all I'm showing is each row is a particular state or community phase, and then also we have conservation practices in here. And these are basically RHEM runs, RHEM output from the model predicting runoff and erosion. These would be relative rates of runoff and erosion for each of these community phases or states, or even the conservation practices. So again, relative measures, not absolutes. But we can also put in here important information we know about each state or each transition or even a conservation practice. So if we apply this conservation practice, we have these relative values for runoff and erosion in the short run, but what are they going to be in the long run? And we can sort of explain some of that here. Within our state and transition model, we might say we're going to apply this practice. This might be our short-term response. Maybe this is our long-term response. We're going to go from here to here. But it's important to know for planning purposes, perhaps, what this response is going to be in the short run. So what's our risk for the different conservation practices we might apply? We might apply a different conservation practice based on our knowledge of those risks. So again, we're starting with the rangeland hydrology and erosion model in that hydrologic functions table. We're essentially populating our conceptual model quantitatively, coming up with a hydrologic vulnerability for those different degrees of surface susceptibility that are represented by the vegetation and the cover and the site characteristics. So we're starting to populate what I think of as sort of this hydrologic infused state and transition model that we sort of started out with, just this hydrologic conceptual model. And we can even populate quantitative hydrologic vulnerability information for the different conservation practices. So what happens when we burn in the short run and then in the long run? And how long does it take to get here? And what's going to be our hydrologic response along the way? You could do that for cutting or mastication that would be applied for this particular site I'm talking about today. For another site, you might have a host of different conservation practices that you would apply. So now we have all the hydrologic information. We've created a hydrologic functions table. We can start to infuse that information into a state and transition model. This is sort of an abbreviated version. You might have a state and transition model like this for a sagebrush steppe site with woodland encroachment. Struggling with the slide transitions. But here we've just put in some quantitative information for a couple of the different plant communities. You could also add it for these different restoration practices that you might apply. Okay, so the model's starting to get a little bit complicated to look at, and I know people have some resistance to that and some think it's favorable. But there are lots of things we could do in terms of populating the vegetation and hydrology interactions here. For example, we can start to include information on early indicators for the at-risk phase. Are we going to see a structural and functional shift there that's important that might tell us we're about to move here? And then what are the hydrologic ramifications of that? We can add these structural and functional thresholds here. We can populate additional information on those thresholds within each of the phases, as well as add the quantitative hydrologic information there. So we're just starting to populate a more informed state and transition model. We could also add things like the rangeland health indicators. I don't show them here, but you could put them anywhere within the model. In addition to sort of this visual depicted model we have, of course, there's a narrative where we would explain some of these things in more detail. But you can start to sort of see where we were integrating hydrology into the vegetation component of a state and transition model as we would normally want to see it. And here I've talked about runoff and erosion, but in the narrative you could also talk about things like soil, water, what's happening with that as we apply the different conservation practices and as we move from place to place in a state and transition model. So by way of summary here, we'll just say that the ecohydrologic relationships are already required in ecological site descriptions, but they're often limited, at least in a lot of the ones that I've looked at. The hydrologic functions, the state and transition model, and the narrative sections are primary entry locations for this type of information. And of course, the RHEM tool represents a new way we can populate actual quantitative hydrologic information within these models and start to inform state and transition models and other community dynamic components of the ESD. And then integrating that information, we think integrating these feedbacks into state and transition models can improve their utility for assessing and managing rangeland ecosystems, at least as we view it and as we outline in our paper, that hopefully will get accepted and in print sometime later this year. That's our hope. This is just a host of papers that we have on the experimental data and on the rangeland hydrology in a model being applied, at least in the context that I'm talking about today. And then if we have time, Mark, we can deal with any questions anyone has.